What's up, people? This is Milos. Welcome back to my channel. In today's tutorial, I will show you how you can leverage the power of Mapdeck and create some awesome 3D dynamic maps of fire events using also NASA firms data. Welcome back to R, where our first step will be to install and then load the packages that we need in today's tutorial. So the easiest way to do that is by first installing a package which is called Pacman. This one will help us easily get the packages that we need and then just load them into R when we're going to do that using this function which is called pload. Now, in terms of the packages we need, the first one is the asset package, which is going to help us work with the simple features or the polygons. In this case, we will have an area of interest that we want to turn into a polygon. The second one is the Terra package, which is going to assist us with working with raster files. And we're going to be working with two types of raster files in today's tutorial. The first one is the digital elevation model, and the second one is the background layer. Now, for the background layer, what we will need is the map tiles package, which has a lot of options from OpenStreetMaps to S3 and some other providers. So once we actually have this, we will also need tidyverse for data wrangling. This is going to be coming very in handy. To fetch the digital elevation model, we'll be using the elevator package, which is going to help us get the tiles from AWS for the area of interest and put them together. There's one additional package that we will be using in today's tutorial, and that is rcurl, which is going to help us actually build the path on our local drive to this digital elevation model, as well as to the background layer, which we are going to actually save locally and then use them to make our 3D dynamic map. Now, for the making any dynamic map, the package in this tutorial that we will be using is a Mapdeck, which has so many things, and I'm going to actually show you how you can add different features and build a very crisp 3D interactive map. And then finally, because I want to show you how you can add fire data, we'll be using a very new package, which is called Earth Data Login. It is going to help us access NASA firms data downloaded locally by just using our credentials that we previously registered. In this section, we will define our area of interest and then use it to fetch the digital elevation model data, to fetch the background layer data, and later on as well, the NASA fire data. Okay, so to give a bit of context why we're making this map is that recently I've seen a lot of fires in California. I understand there are also fires all around the world, but it's kind of made me wonder how we can make some maps that can actually help people on the ground trace these fires and maybe even act on them. And then while I was browsing through X, I bumped into this amazing mounted fire map of Santa Paula in California done by firemap.live, an X account. And this was exactly what I was looking for. So an exaggerated relief map with the background layer and an overlaid with NASA firm's hotspots. So I went to Google Maps, found Santa Paula, and then fetched these coordinates from the URL. And then I went back to R and I pasted here these coordinates. The first one is the latitude, and we will define it as such. And the next one is the longitude. Now, using these two values, we're gonna essentially now create a function that is gonna, first of all, create a data frame out of these coordinates. Second, it is going to then create a buffer around these points and, create an SF object. And after that, we're also gonna get bounding blocks out of this that we can then use for fetching the data, so the terrain data and elevation data, as well as the NASA firms data. So we can get a function which is going to be called, we can create a getBuffer function. And then within this function, what we will do next is create a data frame. So our data frame is going to be composed of two parts, latitude and longitude. Now we want this essentially to be an SF object. So we're gonna also declare that this is gonna be an SF object. And then within this, we need to also specify that we want this to be in a specific shape. So we want this to be points, which means that we need to define then the coordinates. And the coordinates here are going to be first longitude, so long, and then followed by latitude, which is lat. And then last but not least, we also want to define here the coordinates reference system. This is very, very important because otherwise R is not going to know what to do with this data frame, like how to convert it. So we're going to just use the standard WGS 84 coordinates reference system. But this is not all. We now have the centroids, so we converted this into a single point. It's in the SF format. We now want to draw around this a buffer. So for the buffer, we can use st buffer function from SF package. And then over there, we can pass these centroids as cents. And then we need to decide on the distance. So I would go here for not something gigantic because we will be passing this data later on to Mapdeck and getting also the elevation data and the texture in terms of the background layer. So we don't want something huge. We don't know if it's going to be able to render. So it's a very much an experimental feature. So what I'm going to do here is go, for example, for something like, let's say 15, let's say kilometers. So let me just see how this is actually defined. So if you go this to this one, you can clearly see how they do it. So as units, yeah, you need to actually put here if it's meters or kilometers or something. So we can just put here kilometers. So let's say 15 kilometers. And then the last part here is to make sure that this is in the appropriate coordinates reference system. That means the one that we used before, so WGS 84. And once this is done, you can go ahead and here return this circle object. This is not all, however. We also then need to create an object by calling this function. I'm going to call it area underscore SF, and then we can just call this getBuffer function. Now that we have this, what we essentially need is the bounding box for this area that we will then use to fetch the elevation, texture data, as well as the NASA firms data. And to get the bounding box out of this is quite easy because we can use stbbox from the SF package and then pass this area SF to it. So now that we have the bounding box of our area, we can use this definition to fetch all the data necessary for that specific area. And in this first part, what we're going to be doing is getting the background layer. So this is basically this, topographical or street view layer or whatever you call it. So the way we can do this is using the Maptiles package. And I'm going to call this just simply BGMap or background map. Maptiles has actually is simply a client library for fetching all these different background map providers. One of them, which we're going to be using in today's tutorial, is Esri, but there are also other ones like, for example, OpenStreetMaps, and you can also check them out on the Maptiles main page on GitHub. So the first thing is to use this function, which is called getTiles from Maptiles. And then the next thing is, what is the area for which you're going to fetch this? Now here you need to pass the bounding box. Luckily for us, we created this bounding box in the previous step, so you just need to do that. Now the second step is the provider. So if you went to the Maptiles website, you will see there's actually a lot of them. You can see a preview of some of them. And if I actually hover over this one in this VS Code, you will see that by default it's OpenStreetMap. Now, there are also a bunch of other ones, as you can see here. Some of them working, some are not. But what I want to have in this tutorial is something which has which is a topographic map, but also has some labels in the background. So what I'm going to do is I'm going to opt for this one. So Esri World Topo Map. I'm going to go for this one. So I'm just going to copy this, and then I'm going to put it here. Of course, it needs to be within the quotation marks. The second thing, or a third, thing is how much you want to get the details out of this one. So I'm going to get as much as possible. It's only a 15-kilometer radius. So I'm going to go for a pretty high zoom of 14. You can also try and increase it a bit further, but be careful because this is going to increase the resolution of this raster file. And then the problem will be with this that you're going to have problems actually plotting in the later stages, the higher the resolution is. So keep this at a bit lower resolution as if possible. We definitely want to crop this to the extent of our, buffer area. And then we also want to reproject this. That's a bit of a trick. So you want to reproject this to the pseudo Mercator resolution so that actually it keeps the crispness. So that's the first thing. Then finally, we can also go ahead and see how this looks like once you actually, fetch this data. And this is an RGB raster file. So essentially, we need to be using from Terra this function, which is called plot RGB. And this is the map that you should be seeing after actually plotting this. You can also zoom in and you can see barely though the names of the places and also the names of the streets over here. And you can also see that there is a pretty nice already shaded relief that we will just then turn into 3D form. And then the last step is simply to save this raster as an image locally so that we can then call it within Mapdeck. And to save it, we can use from Terra function called write raster. Over here, we just need to specify what is the object we're going to save. So this is going to be our BG map. The second one is the name of it. So we can call it bgmap.png, and this is very important that you specify that it's going to be a PNG file. After that, you need to specify also that the missing ones are actually have a black color, or actually it's a 0. And then also, if you are working continuously with this one and you are checking, different options here and different layers, you can also, for example, put here that override equals true so that you can override and get the latest one that you need. All right, so we have our texture layer ready. Now we just need to get the digital elevation model. And to do that, again, we'll be using the elevator package, which allows us to communicate with AWS and get the high resolution tiles from there. We just need to get a raster function here from elevator. Then for the locations, we're going to specify the area SF, which we previously defined. Then for the zoom, we are again going to go for a bit higher zoom of 14, so we get really crisp digital elevation model values. And then what we are going to go here for, we're going to actually clip this by a bounding box. In a sense, we're going to be having a rectangle of the area, which better fits actually the map than just having for the specific boundary of this location. And then as the last step here, we're gonna coerce this object, which is actually a raster object. We're gonna coerce it into a Terra spatial raster object. Okay, now that we have actually with this one a digital elevation model, and we also have our texture, so the background layer map, we need to make sure that actually they have the same resolution, so that we actually really have the elevation or exaggerated relief for a specific point in place. So to make that happen, we can use a very convenient function from Terra, which is called a resample. And then in this one, what we actually want to resample, we want to resample our digital elevation model, and we're going to resample it using the BG map. The reason why we're doing this is because the digital elevation model is going to be probably larger in size. But if it's actually not the case, then you can also reverse things. I like to actually downscale the digital elevation model using something else. And then the last thing is we need actually a bilinear model, which is here by default, but that is because we have continuous values in our digital elevation model, and we would like to preserve them using resampling. So you noticed after I got this digital elevation model raster file, I didn't save it locally like I did for the texture file. The reason for that is we need to adjust this digital elevation model to a proper 24-bit RGB color values. And the reason for that is because if you're doing 3D rendering like we're doing here, so creating a 3D elevation interactive map, we need to make sure that this is in the proper format. So how do we do that? The first thing we will do is, first of all, we're going to extract the values from this raster file. So let's actually start doing that. I'm just going to call this dm values, and then from Terra, I'm going to be using values. And then I'm going to be passing here this element which we resampled. So the goal is to map all these digital elevation model values into a proper range so that they can be used for this RGB display. RGB is simply red, green, and blue values within your colors of your raster file. So the next thing is to do is start off by actually modifying these RGB values. We're going to start off with the R value. So that's the first one. So for the R value, what we're going to do here is we're going to actually modify it in the following way. The first thing we're going to use is then values, and then we're going to multiply it here by 10. The reason why we are multiplying it by 10 is to scale the elevation data, so these values, to give it a higher dynamic range. So that's the first thing. Then the next thing is adding 10,000 here in value to this then values, DEM values, sorry. The reason for adding now 10,000 to this is to scale the elevation data to give it, to ensure that the values are positive and thus that they fit this RGB encoding values. So that's the next one. The reason also why I'm using here this function floor is that I want to ensure that the result is an integer. So for this encoding, you should not have decimals. So this simply kind of make sure that you get a whole number. All right. And now something specific for the red channel here, because we're working on it. And that is this whole thing that you have here, you should divide then by a specific value. And the value for that is 65,536. Finally, the reason for doing this by dividing this value is we are effectively shifting the bits to isolate the red component here, because R is for the red, in this RGB 24-bit representation, where you have actually 8 bits for each of them. So 8 bits for R, 8 bits for G, and 8 bits for B. Okay, then the second thing is to define or actually rescale our green channel, so G. Now, it's very similar to this one, but there are some differences. So I'm just going to copy here and paste. So this is going to stay because this is simply, just for the rescaling purpose. So it's going to repeat also in the next one. But the difference is that here we are, first of all, going to divide it by 256. And this is because we want to get the green values. But then there is additional thing, which is we're also going to deduct from this one, multiplied by 256, this value of the red, so that we also isolate the red values from our green values. And the final step is to define the blue values. So again, we're going to go ahead and copy this part. Well, at least this part, but this needs to actually change. So we're going to be removing this one. And the only thing that we need to do here is actually deduce the red value, which is multiplied by this 65,000, and then minus the green value, which is multiplied by 256. And what we're actually doing here is simply we're going to taking all the values, and then we're going to deduce the red and green values so that we get only blue values. Okay, so to recap on our previous steps, this is exactly what we did. So we actually defined what are the R, G, and B values. Now, the next step is to take these values and then replace the existing values in our digital elevation model with these ones. So we can do that by actually defining a function here and applying it to this one. We can actually create then layers here. So for the layers, what we're going to do is we're going to apply this list of layers. And the list that we have here is, of course, the one that we created. So it's R, G, and B. And then we're going to apply this list to the raster file that we have. And again, for that, we need to create a function here. So within this function, we can actually go ahead and use a very convenient function from Terra, which is called set values. So this function allows us actually then to map these channel values onto our LF file. So this is exactly what we're going to do, channel. Right? And then the last step here is to, once we get these layers, the last step is to simply rename them And renaming them means that we have actually now 3 layers within this one, because remember, we changed red, green, and blue. And just for the convenience sake, what we can do is change this to R layer, G layer, and B layer. All right, so to recap on this one, after we actually defined our R, G, and B values, we then use these values, we put them into a list, and we just map them onto this elevation raster file, and thus creating 3 actually layers in a single raster file, one for R values, another one for G, and another one for B values. Okay, so once we actually have this, the next step is to simply make sure that this layers is transformed into a proper, Terra format file. So what we can do is we can just call this one layers raster, or rust actually. Let's do that. And then simply from Terra, we can use Terra rust and pass here layers. And this is simply gonna then coerce this into a Terra-friendly format. Once we do that, we are finally ready to save this file. But before actually saving, I just want to show you how this looks like. It's gonna actually look a bit weird, but essentially this is not going to be reflected in the 3D interactive map that we will be making. It's simply going to help us, make all these colors scale properly so that they can be shown essentially as a 3D map later on. Okay, so before we do that, again, this is now an RGB raster layer, or a special raster layer. So we need to use plot RGB, and then we can place here, sorry, so it's not layers, it's a layers rust. So layers rust, and then we can pass here, and then we can plot and see what we got. So what you should essentially see here is that your raster file for the digital elevation model now is rescaled to accommodate red, green, and blue values. And essentially what we did is we just mapped those values onto it and then rescaled the whole thing. So this is what you will see now. Okay, and then the last step is to simply now save this raster file using write raster from Terra. We first of all need to provide, of course, the name of this, layers rust. Then we need to provide the name of this one. So we can, for example, call it just elevation underscore map and use PNG as the file format. Then what is very important here is, you remember, we're here working with 24-bit format of our raster. So we need to also tell Terra that this is exactly the format. So over here in the data type, what we will type is int1u, and this is going to make sure that this is recognized by Terra. And then the last step is to actually a bit compress this file, because it can get actually quite big. So let's compress it, but without losing the quality of this raster file. And for that, we can go for the GDAL within Terra. And then within this list here, we can just say that we want to compress, and we want to compress to this LZW. So it needs to be in the uppercase. And then the last thing here is to simply, if you are again working here with multiple files, you are trying different things, you can simply go ahead and include here override equals true, which is then going to overwrite your raster file locally. So we successfully created the elevation and also the texture rasters. We saved them locally. And in this step, we're going to first of all create a pathway in our local drive where we saved them. And then we can then use that path to load these images into R, where we're going to be building our 3D dynamic terrain map. So let's get started by first of all defining the pathway for our elevation raster. So what we are going to do here is, first of all, we're going to glue together the main working directory where we actually saved our elevation raster as an image in PNG format. And then the second thing what we're going to do here is we're going to provide the name for this image. And the name is the elevation underscore map.png. Now, this is not all, because for that we can use normalized path here. So we can just wrap around this thing with the normalized path. What we did now for the elevation, we're going to also do for the texture raster file. So I'm just going to go and copy this one, and I'm going to rename elevation to texture. And also here, instead of the elevation map, I'm just going to put BG map. So now that we created the paths to these images, the next thing is that we need to encode them in an HTML-friendly format, because the Mapdeck output is going to be an HTML file. To do that, we can finally use our curl package, and especially for it, we can use a function which is called base64 encode, which is going to help us with that. Now we're going to start off with the elevation one first. So I'm actually going to go ahead here, and I'm going to create here object called TAXT, because essentially this is just going to be the encoding text for this image. That's it. Now to do that, we first of all need to here read it as a binary file. So that means we need to provide several things here. First of all, elevation. Second, it needs to be in a raw format. And then we also, as a third thing, we need to provide here file info for the elevation itself, where we actually want to grab the first element, which is size. And then the very last thing here is we want this to be returned in the text format. Now, the reason why we created this is that then what we want to do is we want to append this one with some additional info, which is then going to help us get the data in the appropriate formats. So I'm going to call this elevation data, and then we can use to glue together this printf. We can of course use first of all this newly created txt object, and then we also need to provide one aligner here, which is going to say the following. So the data is image, and the image is the PNG format, and this PNG format is using this base 64 encoding for our image. And then we're going to do exactly the same for our texture file. So I'm going to go ahead here and I'm going to copy and paste. And then essentially it's the same thing. So instead of just elevation, I'm going to be using texture here in this, remaining chunk. So we can just replace, but essentially it is the same. It's going to be the same effect. So now that we have the pathway to the encoded images, we can go ahead and start playing with Mapdeck and see how we can actually create this 3D terrain map without any additional data. So to do that, we can first of all go ahead and call Mapdeck. Mapdeck is going to help us then essentially call this Deck.gl library. So we can go ahead and do like this, Mapdeck. Now this is the main one, like the same way you're using ggplot to call to create actually a map, you also need to do a Mapdeck and then the Mapdeck function from this library. Now, what I'm going to actually do here is I'm going to assign this to an object, and I'm going to call it terrain 3D, because I want to save this as a separate HTML file. I'm doing that because you can then use this HTML file and you can embed in your own browser, on your own website, whatever you want to do. So the first thing we want to do here, this is kind of the macro option. Essentially, it's for the general settings of your 3D interactive map. The first thing you want to do here is you want to define the location. So this is where the zoom will be, and this is going to be the focus of your map. So we can just go ahead and use this longitude and latitude coordinates that we defined at the very beginning, if you remember. So this is going to be the area of Santa Paula in California. Then there are also other things you can define that are very useful. This is going to be the zoom level. So what is my maximum zoom level? For example, let's say 15. This is going to be, so the higher the value for the zoom, the more you are zoomed in into the map. And I would like this to be kind of a zoomed in quite a lot. So I'm actually going to go ahead and choose quite high minimum and maximum zoom values for my 3D interactive map. Then there is a function which is called bearing here, and bearing. So bearing in this concrete sense, if I go here, you can see that it actually does, it can actually rotate your map essentially around the z-axis. So I'm actually going to choose 0. I don't want to rotate it, but this is if you want to, from a specific angle, to have that. Then we can also define what is going to be the angle of not just of the scene, but also of our object. So this can be done using min and max pitch. So how much is pitched your scene? So we can go, for example, let's say 60 degrees, and then for the max pitch, we can go 120. This is, as you will see, is like essentially it will kind of rotate it in such a way or define the angle in such a way that it's kind of you will be able to see the height very well, as if you're kind of walking into the scene itself. Now, speaking of the height of the elevation itself, you can also define that, and there is an option which is called height, and this is defined in pixels. So you can go ahead here and type, I don't know, for example, let's say 1,000 pixels. Because this is pretty much an experimental feature, adding this terrain and then elevating it, I found that if you increase beyond 1,000, it's not really going to change, and at some point it's not even going to render your map. So I would say tread carefully with the height and choose something that is around 1,000 pixels. You can decrease and see. But if you go down to lower values, let's say 100 or 200 pixels, then it's going to become more or less flat. So you won't have this kind of a feeling of the 3D scene anymore. Okay, now with this done, this mandatory parts of the general settings, we can go ahead and then add terrain. And adding terrain is done through a function from Mapdeck, which is called also add terrain. So add terrain, as I mentioned before, it's pretty much, it's a quite new feature. So it's an experimental stage, and it's not something, that is so much stable at this point, as it might throw error or you might not even render your scene in some cases. So again, tread very carefully. One thing that we want to define here is the path to this encoded image. So essentially what we're going to do, we're going to provide this elevation data that we created previously. Okay, with this done, there is another important thing, which is you need to provide, or you don't need to provide, but in our case we can, what is going to be the texture. So this is going to be the upper layer, the one that is, thanks to this one, is going to get extruded. So this is our background map, the street view layer map, if you remember from the beginning. For this one, we also have the pathway, so it's called texture_data. Now there is one important thing now for the elevation. So as I told you before, it's a very experimental feature. So there is a way actually that you need to set it up so that you can see properly the 3D version, and also you can see the color and everything kind of in a proper way. It's called elevation decoder. So if I go actually and hover over the elevation decoder, I think it's not going to show up, but if I go here, so the elevation decoder, it's essentially going to be 4 values used to convert a pixel to elevation in meters. So this is going to be your red scale, green scale, blue scale, and then the offset. Now, essentially, offset is how much it's going to be, offsetted or extruded in this case. Now, this I took from the Deck.gl website, these values, and it's really helped me to create what I wanted to create. If I went for this map that adds terrain, the default one, which was, yes, 1 null, it didn't really do the job. Actually, it created some really weird stuff there that were really extruded. So I actually used these 4 ones, and I copied this and pasted directly from the website. There are a few other things that we can also add here, and one of them that is pretty useful is to create bounds. So I actually started writing here. Bounds essentially is those 4 values of our bounding box. So the minimum and maximum latitude, longitude values. This is going to help actually our interactive map be focused on this specific area. And over here, we can simply use information from the object that we previously created. So that is our bounding box. And we need to start actually here with a minimum longitude value, so that is x min. Then we need to provide here, so it needs to be in a specific order. The next one is going to be minimum latitude values. And then the last thing is we want to have actually maximum longitude and maximum latitude values. And now that we have bounds, we can go back over here to add terrain in our map deck, and we can use bounds and pass to it the object with the same name, which is also bounds. And that is not all. Like, there are also other things you can see here. There are several things. One thing that I like to add is the max error. So the max error essentially is how much you will tolerate the error in your mesh. And the lower the number, the crisper your mesh is going to be, but also more complex. Or in the end, your HTML file might be actually too big. essentially, I think the default one is 10, and we can just, decrease it a bit further to 5. And then once this is actually done, we can go ahead and, render this one. But essentially, if you want to get an HTML file, you need to go ahead and do a bit of more coding. So we can use HTML widgets package, which you didn't install at the beginning. I suggest that you add at the beginning to the pacman pload so that you can do that. I already have it installed. And for that one, there is save widget option. What we're going to do is we're going to pass this terrain 3D, so map deck object. Then we're going to name it somehow. Let's, for example, just use the standard, index.html. And then this is very important. You want to have self-contained equals false, so that actually it just saves the HTML file, but also any additional files in a separate folder. And this is what you should be seeing if you did all the steps in a proper way. If you actually zoom in, you will see there is also an elevation. And you can also see that some of the names here are a bit twisted, and that's because we elevated this raster file. Moving on, we can see also the names of the places, the names of the streets, parks, even some roads and rivers, as well as mountain peaks. But I think the main thing here is that this is now the thanks to the elevation layer that we have beneath this, all those features that are mountains that have been now elevated. And if you actually go here to north, you can see how much some things are just too tall. One thing you will notice if you go to the edge of this 3D interactive map is this a dark gray layer. So this is essentially the elevation layer, which is beneath ours. And in some cases, it does not completely perfectly overlap. So this is why you can see this. And essentially, thanks to this dark gray layer below this background map, it's possible that we now see, this exaggerated relief the way we see that. And this is not all that you can do with a map deck. You can also add some other layers. You can, for example, add polygons, you can add lines, and you can add even points. And this is exactly what we are going to be doing in the next step. We're going to be adding fire points. So all those fires around Santa Paula for a specific date. And for that purpose, we'll be using NASA Firms data. NASA data is hosted at Earth data page, and the first step we will need to do is register there. This is a free service, so you simply need to leave your email, your password, and then you need to click on register. And the easiest way to do that is to simply follow one of my previous tutorials where I explain this in detail how you can do so. Once you have your email address and once you have your password, we can go back to R and then use this information to fetch the NASA Firms data. But before we jump into fetching the data, I am here at the NASA Firms website, and I'm going to show you how you can actually get the archival data. So from my previous tutorial, you learned probably how you can get most recent, no older than 7 days. But over here on this website, there is something from which you can actually download this archival data, and that would be this link. We can just click on this link, and this is then going to open up a new window. Of course, it's very important to stress again that you should already have by this stage your Earth data credentials, so your username and your password. All right, then we can actually choose which satellite we want to use for the fire data. I'm going to be using this one, NOAA21. VIIRS data. So I'm going to just click on this, and then it's going to ask me which continent I need. Because we are here working with data from California, we need this one, which is called USA, Contiguous, and Hawaii. If you're working with some other place on Earth, you should choose one of these. And if you're not sure, you can always go for global, but that file is quite large. So I would always encourage you to specify based on the area that is specified here. So we're going to go ahead, click on this folder, US, Contiguous, and Hawaii. And over here, what you will get are files for almost every day of this year up to the most recent day. So today that I'm filming this, 15th of December 2024. So we can see actually the data for the entire 2024. All right. Now, we are not interested in all the data. What was happening in Santa Paula was actually the beginning of November. So essentially what I'm going to be searching here is the data for November 2024. So that would be the 11th month. And what I would actually like to do here is probably search for something like data from, let's say, November the 1st, and then going to all the way to, let's say, November the 10th. So we can get data something like this. Now, what is important here is to understand what is the link. A link you can obtain from this item over here, which is the download one. If you just go ahead, right click, and then copy link address, it is going to copy this link. Now, instead of like copying link for all of these dates, so from the 1st to the 10th of November, what we're going to do is we're just going to use this link that we just now have, and then just we're going to append it. One thing that you can notice in all of these URLs is that they're the same until this very last part, which actually tells you, what is the number of it. So 2024 305. So this 305 is essentially just the number of the file. So in our case, what we would need is if we want to get data for November the 1st to November the 10th inclusive, we would need files from 305 to 314. So we can easily then create from this one URL, we can create all these URLs and then just download them to R. So let's actually go ahead once more. Click on this item here and then copy link address, and then we can go back to R and do what we need. So going back to R, I simply pasted here this link that we previously had. And one thing that you will actually notice is that this thing at the end, we will actually need to recreate it. So what we will do is we're going to create, based on this one, we're going to be creating a main URL, which is going to be a text object. And then to this one, what we're going to paste essentially until here. So it's going to end with 2024. And the reason for that is that the file number, or the ID as we call it here, it actually varies. So as I said before, we can, for example, we don't need to start from November the 1st. We can, for example, start from November the 5th. So that would be file number 309. And we want to finish with November the 10th inclusive. So that would be file number 314. Remember, this is from the previous view. And then having this two information, we can actually create all the URLs that we need. And for that, we can use the paste from base R. Then we can, first of all, provide this main URL, followed by ID. And very importantly, there is one small part at the end, and that is .txt, essentially telling us what is the format of these outputs. If you quickly inspect, you will see that we now have actually 6 links here that we created. And then the next thing will be to connect to the Earth data and so log into the service and then download these files locally. Connecting to Earth data and download it used to be a pain, but there is a new package, R package, which is called Earth Data Login, which is going to help us do this in no time. The only thing we need to do is just provide our username and password, and then use this information to download all these files locally. So we can go ahead and use this package that we previously loaded into R and of course installed if we didn't have it. Then we can use this EDL net RC. This one is used for authenticating yourself. So you need to provide 2 things. One is the username. And then over here, you should provide, of course, your own username. So I have my own. I'm not going to reveal it here. And the second thing you need to have is your password. Again, it needs to be in the text format, and I'm not going to be revealing my password. So you should replace username with the appropriate username and your password in this Earth data that you filled to register in the previous steps. Once you have this, you just need to apply to these URLs that we previously defined another function from this Earth Data Login package, which is called EDL download. So this is then going to download locally all these files to your working directory. Displaying the first few rows, you will see that our data is in the data frame format. It has several fields. So the latitude and longitude, these are essentially the coordinates for every fire occasion or a fire event, to be more precise. Then we will be also using this bright TI4, which essentially tells us how bright are these events, meaning actually how strong the fire is, to put it in more kind of a lay terms. And the rest we don't necessarily need, but you could also get, for example, when the data was acquired, which is essentially going to tell you then what is, for example, the date. But for now, we're just going to be using the latitude, the longitude, and this bright TI4. The easiest way to pass this to Mapdeck is to turn it into an SF format. And this is exactly what I'm going to be doing. So I'm going to create fire points SF. And then, as we did before, I'm going to be using STS-SF from the SF package. That is the way to turn a foreign object into an SF object. Then we're going to pass here combined data. And as you remember from the beginning, when we were creating that buffer, we need to provide here the coordinate names. In this case, also, if you remember, we need to first define the longitude column and followed by latitude column. In our case, they're called longitude and latitude. And this is what we are actually defining right here, longitude and latitude. And once we have this, it's not over, because we also need to set the coordinates reference system. And because we are using here the 4326, we can also define it here. So for example, 4326. And last but not least, we also want to make sure that we include of all those fire points across a United States, contiguous United States and Hawaii, only those for our area of interest. So that would be the area around Santa Paula in California. So to do that, we can simply intersect all those points that we have with our area underscore SF, which we also defined at the very beginning. Then before we go on and map this data, what we can do is a bit of data wrangling just to modify certain things and make them in a proper order. So we can pass this one over here. And one thing that we will need to do is we will actually need to modify a bit that brightness column that we'll be using for different colors, because currently it's in Kelvins, and we would actually like to have it in Celsius. So the way to do that is the following. We will need to modify it using mutate function from a dplyr, which comes again from tidyverse. And then we're going to be using, so my mistake, not bright underscore TI4, but bright underscore TI5. Regardless, the way to actually then convert this from kelvins, which is the native units, is to use this formula. So this original one minus 273.15. Once we have that, one last thing we can do is again call to rescue dplyr and its function select, which is then going to help us select only those fields that we need. So what we need is essentially only bright TI5. We don't necessarily need also other. And finally, what we can do is all the missing values, we can simply omit them from our data. Now, one just thing of caution here, it might be that this bright TI5 was not properly converted into an integer when we were actually transforming this into a data frame and then the SF object. So you can just make sure that it is by placing here as numeric around this bright TI5, and then that should do the trick. And this is just like the screenshot of the first few rows of this data. As you can see, we have this bright TI5 in Celsius. And then we also have the geometry field for our SF object, which are points showing the locations of fire events for our area of interest. Okay, so we are now moving back to this area where we were coding the 3D terrain, and we are now going to append this code and add the part where we have we're going to add points. So there is a very cool function from Mapdeck, which is called add point cloud. Now, add point cloud if you're not sure what it does, essentially it takes your points and then puts them into the scene, and you can also kind of elevate them if you need. That's why it's called point cloud. For the data, we are using this fire DF. Essentially, it's an SF format. Then you can define some other things. But if this is an SF format, you don't need to, for example, define X and Y values. If, however, this was in a data frame format, you would have to do that. So this is very, very useful. Then you can also decide how big these points are going to be. I'm just going to go for 5 radius. You can increase or decrease, see what works for you. You can add also, of course, some other things. For example, you could add tooltip, but we don't have some additional information. Tooltip could be added, for example, for the date. So you could also see that. Maybe we can add that in the next step. But for now, I would like actually to fill these points based on the value of this bright underscore TI5. And then you can also choose the palette that you need. Now, there is one cool thing here. By the way, I'm going to go here for the heat palette. But there is a way actually to check what kind of palettes are available. And I'm actually just going to do it just below here, just to show you. So if you go, for example, for this, there is a package which is called color values. I don't know if you have it installed. If not, you can also install that. And then you can choose this color palettes. This should actually give you what are the names of all the possible palettes that exist. So if you just kind of run this, I get here more than 50 values. And one of them that I'm going to be using from this one is the heat palette. But as you can see, there are a bunch of them and you can play around and see what works for you. So going back actually to this one, we are actually done here with the code. I mean, there are, again, lots of different stuff, lots of customization points here that you can see. You can even use the highlight color and, you know, some other things for legends, the way you're going to define. We're going to get the legend here, but you can also define that. You can really play with that. The next thing what we will do is essentially just run this entire code and get this index.html file in our working directory and then see what we got. Opening your file in the browser, you might be wondering where those points have gone, but actually if you zoom in, you will see a slight contours of them. Essentially what happened is, because we have here an elevated 3D layer, we did not really define what is going to be the height level for our points. So they were actually plotted on the same height, but because we extruded this entire layer, they were kind of ended up being buried down deep below this layer. So I can just see here some of the contours. So this is a very suboptimal situation for us. I don't want to say bad, but suboptimal, but it's fixable. So we can actually go ahead and definitely fix that. What we need to do is we need to calculate for each of those points what is their altitude, and then we need to put that back into that SF object and then provide this information to Mapdeck so that can actually properly plot each of those points and have them above the ground. To make correction, we will need to go back where we created this fire underscore points underscore SF. And over here, we need to do one small thing, which is we're going to calculate here altitude. Altitude is easily calculated if you use extract function from Terra. What you just need to do here is define several things. First of all, what is the elevation? So in our case, that would be this elef object. The second argument is going to be what is the another object for which you want to calculate elevation. So our points. So that would be this fire points underscore SF. And then finally, what is going to be the function that you're going to use? I mean, here it doesn't really matter what you put. You can also put here maximum ones. So then once you actually calculate this altitude, you're essentially going to get 2 columns. And the second column is going to be the one that has all those values, Z values. So then what we're going to just do is from this altitude one, we're going to grab this second element. Okay, but this is not all. So now that we have these Z values, we need to actually integrate them into this fire DF. Okay, so that means we need to create here another column. So we can just go here in this part where we were updating or modifying this bright TI5, and we can add another one, which is going to be our Z value. So Z value. But one thing that is actually pretty useful is if we maybe a bit increase here the elevation. So I went for like 100. Maybe in your case, you're working with a more flat ground, so you can even have a lower value, or maybe if you're working with very, very high mountains, high mountain ranges, you want to increase this value. I'm just using this kind of to give even more visibility to our points. Okay, and then one last thing is we need to also add here Z value to the list of columns that we are going to be selecting. And before we go ahead and change our Mapdeck codes and add the elevation, I was thinking maybe we also want to create a tooltip so that you can see how a simple tooltip looks like. So in this columns that I want to include, I'm also going to choose this one, acquire date. So you can also then see how that works. Anyways, once this is done, we can go back to this step number 8. And again, we can modify our script for the map deck. There's not actually much to do. The only thing we need to do here is define what is our elevation. So that would be the Z column. And then one thing also we can do is, for example, we can define the tooltip. For the tooltip, we can go ahead and select this acquired date. And this is the final 3D dynamic map of the exaggerated terrain. Using Mapdeck, now you can clearly see all those fire points in different colors, indicating their brightness levels as seen from the satellite. And you can also see the legend in the lower right corner of the screen. One thing that you can also notice is that if you hover over any of these points, you will see also the date time when this was recognized or actually captured by the satellite. And this is how you can create a very crisp 3D dynamic maps with Mapdeck and also add some very useful information like NASA firms data that we did. I'm very curious how you use this for your own project and create some awesome 3D dynamic terrain maps with Mapdeck. If you're interested in creating or recreating today's map, I prepared a link to the GitHub repo in the description box below. So do check it out. Feel free to clone it, reuse it, modify it as you see fit. If you're new to R and you seek to expand your data visualization and GIS knowledge, which are, I prepared a few cool tutorials for you. So do check them out. See you next time.